anti-islanding. I'm sure a lot of you have heard of that. It's a very common concept used for PV inverters, solar inverters, and wind inverters as well, but primarily solar inverters that come in small power levels and go up to large power levels. So we're focused here today on using the AZX product family for this. It's our larger power system, and it has all the regen capabilities to do these kinds of testing. So what does anti-idling mean? It's really a mechanism that prevents the energy from being energized when there is a utility power failure. So when part of the grid de-energizes for whatever reason, could be natural disasters, could be storms, could be arcing somewhere in the grid. When that happens, any what's called DER, or distributed energy resource, that's connected to the grid and synchronizes to it, has to be able to detect the disappearance of the grid connection and act accordingly by disconnecting, disengaging, and stop putting power on that as part of the grid, so that it's no longer energized. Because when there is a power outage, usually the utility obviously sends out a crew, a line crew, to go and restore power and repair any damage so the power can be restored. And when these guys are working on that part of the grid, they expect it to be de-energized, of course, because it's down. If these DRs that are connected, it could be your home PV and solar installation, is still putting power back on that section of the grid, it's extremely dangerous for these line workers. So any PV inverter or any other energy producing device that pushes energy back onto the grid, like a PV inverter, solar inverter, wind inverter, has to meet certain safety criteria having to do with anti-islanding, and it means they need to stop pushing energy on the grid, on that section of the grid, when that happens. So these standards are controlled by states and regulatory and as well as utilities, and there's some standards that apply to this. Some examples are listed here: UL 1741 or IEEE 1547 or IEC for Europe 62116, and they all have similar objective, is to be able to verify that a PV inverter or any inverter that is connected to the grid has the ability to detect an anti-islanding condition or a condition of the grid disappearing and disengaging or disconnecting when that happens. So the test setup, for that is simplified on the right-hand side. You see the grid simulator that will simulate the grid for test purposes. Then the unit under test, any PV inverter or any regenerative inverter. And then in between, you need a LRC load bank or load that simulates the grid impedance. So because that's usually what happens when the grid power goes out and there's other energy sources connected to it, they will see an impedance and they will feed that impedance. So it will actually continue to push into that. And that's what is being simulated here, to see what would a grid condition look like when that happens. So in order to do that, you have to simulate those conditions using an RLC control bank. So if we look at some key applications for this, we'll go into a little more detail on that test setup next. But it's a mandatory requirement for distributed energy resources. So it's not an option. You have to do a type test on any inverter model, and has to be certified. And it's not something you can typically do yourself unless you're a large company, you have the resource to do it. So most manufacturers will go to a third-party lab like UL or any other test labs, recognized test lab that are certified to do these tests. And examples of DERs are listed here. Obviously, solar inverters are very common. EV chargers are more and more becoming bidirectional in the last few years. So they are now essentially also considered DERs when they are plugged into a charger, a bidirectional charger at home or at a other facility. And as such, they are potentially energizing the grid as well. When there is a power outage, they also need to meet these anti-islanding requirements. So the demand for this test has grown from just inverters, PV inverters, to also more and more include EV chargers, bidirectional chargers, both onboard chargers as well as home chargers that are often used in combination with battery backup system to provide backup power to the grid when the grid disappears by using the battery in the car as storage. So another category here, of course, are battery backup systems or energy storage systems that are used to supplement grid power. they again are also sinking to the grid and pushing energy back when there's a need to do so because of demand. But if the grid has a functional failure in a section, and you don't want that battery system to keep energizing that section of the grid when there is a line crew going out to repair it. So those are all categories of DERs that have to meet these similar standards in order to be fully compliant with that. Looking at the actual test itself, as I mentioned earlier, the test stub typically consists of an AC source that simulates the grid or grid simulator. Because this is a DER test, their energy has to be able to flow in both directions. So you need a regenerative source for this, typically. The EUT, in our case, is going to be a DER that, like a PV inverter that pushes energy back. This test setup example here, we're showing a three-phase DER, but it can be a split phase or a single phase as well. So it simplifies test setup on single phase. This is a full three-phase setup, so I can handle any type of DER, depending on the power level, of course, of the power the grid simulator. And in between, you have the RLC network, which typically has to be adjustable. So, and traditionally, this has been done with a combination of inductors and capacitors and resistors that are switchable, that you can basically reconfigure from one set value to a different one. So it's cumbersome. It dissipates quite a bit of energy, especially the resistive components that are in there. At high power levels, it's a certain amount of energy need that's going to be dissipated and put into the air. So, not a very efficient way of doing things, but historically it has been the main way of getting this setup done. And we'll be looking at using our electronic loads for that in the next few slides. So, but this is a traditional setup, and you see on the left you have the ability to disconnect the grid simulator, meaning that simulating a grid power failure, and the objective then is to determine how quickly the EUT is able to disengage. So it has to be done within a certain amount of time, and if it misses that time window, then it's considered a failure. So there we have the typical test setup. This one is provided by the IEEE 1547.1 standard document. And if we look at closer look at the the load that is in between the grid simulator and the DUT, it has to obviously be able to handle the power levels, the maximum power level, and it has to be adjustable. So the values are not fixed; they may have to be set to different values for different test conditions, and of course, it has to work in real time. So what typically is done in the past, as I mentioned, are using load banks, RLC load banks that are complex in terms of wiring and adjusting. They're not easily programmable, so it's not a very convenient way, and that's where using an electronic, load emulation or load simulation can be of a significant advantage. So, and we'll see that in a subsequent section. This is what a anti-idling test would look like if you looked at one phase. You would basically be running normal operation. At some point, you would basically disconnect the output of the grid simulator, so the output would go away. At that point, the voltage and the current will still continue in the RLC circuit, fed by the DER. But the DER has to be able to detect that this condition occurred. Generally, when the grid disappears, and the grid is normally providing the synchronization of everything, these DERs will start wandering. They'll start, frequently will start deviating. The voltage will start deviating because there's, potentially one or more DERs connected to it, and they are interacting with each other at that point. So when there's no longer a grid that keeps everybody in sync, they will basically start seeing some deviations of the frequency and voltage, and they have to basically detect that quickly and respond accordingly by disengaging. So at that point, they will disconnect, and the voltage should collapse at that point completely as the test setup is now de-energized on both sides. And at that point, the test setup will detect at what time that happened from disconnection to the grid. So that time window is critical and has to meet the test requirements of the standard. So The example, of course, of this test process is to run the setup with the grid simulator connected, set the RLC for the correct load, so it is in balance, and then to once everything is running in a steady state condition, is to perform the grid disconnect. It can be done by a physical switch, or if it's a programmable grid simulator, it can be done by programming the voltage down to zero to simulate a loss of grid, and then monitor using measurement equipment, typically a scope or a power analyzer or something of that nature that can determine time domain information of the voltage and the current, and monitor the time that it takes for the DER, the UT to disconnect or disengage. So, and that trip time has to meet the test requirements. So that's the sequence of events, and very often you'll have to do this under different load conditions. So in order to accomplish this, there's a number of things that the test equipment has to be able to do in order to perform these tests. First of all, it has to meet the grid simulation requirements in terms of voltage, frequency, accuracy, and stability. So in order to meet the requirements for the IEEE or UL and IEC standards, so it has to be accurate enough to do that. It has to be programmable, obviously, to simulate different grid voltage and frequency combinations. So you have the ability to test for any region or country. Also means you need to be able to support, both 120 or 240 or three-phase 400, 380 or 480 volts. Typically 50 or 60 hertz is most common for DERs because they're grid connected. And so you have to be able to programmable all those functions accurately. You have to support enough power to run the test setup, and so you need sufficient voltage, current, and power ratings on your grid simulator, and you need to be able to disconnect the grid power, as well as if you're using an electronic load, you have to be able to control the load impedance RLC components accurately. Some of these tests, are relatively fast. I mean, you're looking at, disconnect times that are, less than a few seconds. So you have to be able to capture that event accurately enough to measure the time accurately. So that's generally done by either some of the test equipment you have, and typically oscilloscope is the best, one of the common ways to do that. Phase programming, obviously you want to do both single phase and three phase, and being able to also simulate unbalanced phase conditions to see if the inverters act accordingly and handle that properly. So you need fairly variable phase angle control. Powerful controls of the power source of the grid simulator to do immunity testing of voltage anomalies such as over and under voltage, frequency jumps and shifts, phase imbalances. You want to be able to simulate all those for testing DERs as well. If you want to automate some of these tasks, because they can take a long time to perform, if you want to run them in sequence without minimal user intervention, you have to program that. So you have to be able to remotely control all the test equipment, and because there's multiple pieces of equipment involved, you generally will need some sort of a ATE program or scripting program that interacts with all these pieces of equipment, the scope, the grid simulator, the electronic load, to get everything collected correctly and performed and integrated. Sometimes you need equipment other than power sources and loads, such as scopes and power analyzers. So there are some companies that specialize in this kind of integration, such as Quality Logic, that develops these kinds of scripting software and also implements all the requirements for the various UL and IEEE and BD standards. Flexible multi-channel configuration is nice if you're dealing with both single phase, split phase, and three phase DER testing. If you're a test lab, you want to be able to handle all kinds of DERs, preferably. So you want the ability to have different phase modes on your equipment. So those are all important criteria for the requirements of the equipment on the test setup. So the AZX series of products consisting of the AZX full featured, all-in-one, or the GSCs, grid simulators, and the ELZ electronic load products, meet all these requirements. So they are a good candidate for these kinds of test setups. They are all regenerative, so they're very capable of managing the power flow in both directions. The built-in measurement scope capabilities are high resolution, down to 10 microseconds, so they can accurately capture the time between the grid disconnect and the DER turning off. So you get a good capture of the voltage and current, as well as the time that it took to accomplish that. And then, the scripting, of course, is available to scripting commands on these units as well. And it also has external trigger if you want to use external scope or test equipment, measurement equipment as well. The load capability of the AZX or the ELZ is able to simulate RLC networks. We'll see that in the next section of this presentation. It has the ability to program RLC components individually, including different values for different phases in three-phase or split-phase setups if needed, and it has very fast transient response. So it has a very fast regulation and transient response capability with an inherently low output impedance to simulate high power grids with low output impedance. So that's one of our primary solutions for some of these test setups. This is an example of the built-in web browser function, Smart Source, that will allow you to monitor the output of the grid simulator. And a similar screen is available for the load. It'll show you the voltage and current on all phases and the frequency, as well as the power and the reactive power. And it also includes the scope capability. In this case, on the left, you see steady state condition before the test. And then in the right-hand side, you will see the effect of disconnecting the grid power. You see the time measurement that it took to determine how long it took for the DER to disengage and basically voltage drop to zero. So very convenient to have all that integrated into your test equipment. So the AZX series is a power system that is available in a single cabinet starting at 30 kilowatts up to 55 kilowatts of power. It can be paralleled up to 10 units to 550 kilowatts. It's a three-phase system for higher power applications. They can be configured up to 1.1 megawatts for very large DERs. It's a full four-quadrant regenerative power with a 90% efficiency, so most of the power will be able to be returned to the grid, especially convenient for load applications where you are absorbing a lot of power, so you're not wasting it by burning it off, but you're actually returning most of it back to the domains. So that will save quite a bit of energy over time. Wide operating environment for voltage and frequency, so you can program up to 480 volts line to neutral or 830 volts line to line, so you can handle 600 volt grids as well as 480 volts and 400. And for DC applications, it has three outputs up to 680 volts DC each. So it allows you to do both AC and or DC type testing. Overcurrent capability for short periods of time to write through inrush currents, and the ability to not only run single, split, and three-phase, but also combine multiple channels. So if you had a single-phase DER, you could use one channel for a grid simulator and a second channel for the electronic RLC load. So you could do a test setup with a single unit. So very flexible in that sense. Load is an option on the grid simulators, or you can also add a dedicated electronic load version, the ELZ model, which acts as an electronic load only to create your test setups. And all these models are controlled from a web browser interface called Smart Source Suite, which doesn't require you to write any software or use any instrument drivers or any other resources to be able to access and program and control these units remotely.